ACI, the Network Made Simple learning series. In this video, we will cover Module 3, Configuring Logical Connectivity, Chapter 1, Understanding the Model, Part 2. In Part 1 of this chapter, we cover the first 3 steps in order to configure the logical network in ACI. Now, we will cover contracts and an overview of L3 out EPGs. Remember the fundamental rules of the game. Same EPG, communication is allowed by default. Different EPGs, a contract is needed. And like everything, remember there are ways to modify this default behavior as covered in Part 1. Let's continue then with Step 4. Before, we would need to create access control lists in order to block or permit traffic on a per port per switch basis. We would need to specify things like source and destination subnets, ports, and more. Then, we would apply that access control list on a specific port, inbound, outbound, or both. Now, with ACI, we create contracts to define communication between endpoints in different EPGs. We just have to create a contract once, and ACI will deploy it consistently across the whole fabric. We don't need to specify source or destination subnets, only protocols and ports. ACI follows a whitelist model. Therefore, you need to define what you want to allow, and then the rest is denied automatically. Contracts are bidirectional by default. However, you could specify different filters for each direction if you need to. In ACI, we define the direction of the traffic by specifying source and destination EPGs, which are known as consumer and provider respectively. Consumer is who initiates the connection, and provider is who receives it. For example, if I SSH to a server from my computer would be the consumer, and the provider would be that server receiving communication on TCP port 22. Let's see all this in action then. If we remember, in Part 1, we defined an EPG called Web and mapped Web Server 1 and Web Server 2 VMs to it. Now, we will add a database VM, which is running with IP 2223 as you can see, and it has 2221 as its default gateway, which is currently not responding as it hasn't been configured. Let's then create a new EPG for it called DV and create a bridge domain associated to it. We'll place the bridge domain in the same VRF we previously created, and we will assign the 2221/24 subnet to it in order to serve as Anycast gateway for our database VM. Done. We can always verify that the DB bridge domain was created along with its subnet in the corresponding section. Now, as we did with the web EPG, we will also associate it with our VMware VMM domain, and we can see that a corresponding port group was created on vCenter with VLAN ID 2129 this time, which was also assigned from our dynamic VLAN pool in the physical network configuration. Let's now assign the DB EPG to the database VM and ping the bridge domain IP, which will be serving as our Anycast gateway. It works as we would expect, since this IP is programmed in any leaf that needs it. We now have 2 EPGs with different VMs assigned to each of them. Let's try now to ping the Web Server 1 VM from the database VM. Will there be communication? Of course not. Why? Because as we said, the second rule of the game is that endpoints in different EPGs cannot communicate by default unless a contract is created. Let's leave that ping running continuously, and in the meantime, we'll go ahead and create a very simple contract that specifies that endpoints in the web EPG can talk to endpoints in the database EPG only if traffic is ICMP based or if it is targeting TCP port 89 on the DV endpoints. Since this is a whitelist model, all other traffic should be dropped. Within your tenant and application profile topology, simply drag the contract icon to your source or consumer EPG, which in our case would be the web EPG, and then from there, drag it to the destination or provider EPG, which would be the database EPG. As you can see, we can identify who will be the configured consumer and provider EPG in the top part of the screen, and swap roles in case you made a mistake like me. We have 2 options here: create a new contract or use an existing one. In our case, we have not created any contracts for this tenant yet. So that means that we would only see contracts from the common tenant if we have any there. Instead of reusing a contract from common, let's create our own. Add a name to the contract, and then notice we could simply allow all traffic if we wanted to, or we could add specific filters within it. If you select Allow All Traffic, you will be using the default filter from the tenant common, which allows all traffic. This is one of the reusability use cases for such tenant and its objects. In our case, we won't make it that boring. So let's specify two filters allowing ICMP traffic first, and then allowing traffic sent to the destination or provider's TCP port 89 as shown in the diagram. Traffic is not flowing yet, as you can see, but in the moment I hit submit, traffic starts flowing between my web and database VMs since the contract is now applied. I really don't care if I only have 2 servers or 50, or if I have 2 leaf switches or potentially hundreds even in different locations. The same contract configuration is created once and pushed simultaneously everywhere, enforcing the policy consistently. Any policy change you do afterwards in the contract will also be applied simultaneously everywhere, making ACI contracts way more effective than configuring ACLs on every switch and port as we used to do. We can verify the applied policy, where you can see which filters have been applied, as well as who is the consumer or provider based on the colors, or by going to each EPG and clicking on the contracts folder for each of them. Let's now minimize our EPG folders, and then you can see there is a contract section per tenant. Here, you can also see the contracts created overall for this tenant, as well as the filters associated, which you may reuse as well in other contracts if you need to. As you would imagine, that same contract you created once will also be used for any additional domains you associate to your EPG. So, if I add Hyper-V database servers, additional bare metal servers and switches, or even if a VM is moved to a different server on a different leaf switch as part of vMotion, they will all follow the same policy as defined in the contract without further configuration. We will see some bare metal to VM communication examples when we cover ACI integration to legacy environments as part of this module, so stay tuned. With ACI, you can also configure a special type of EPG called microsegmented EPG. This is useful when you want to automatically associate an endpoint to an EPG based on its attributes such as IP address, operating system, tags, FQDN, name, and more. For example, if your web server suffered an attack and you needed to isolate them from the network as soon as possible, it would take a long time for you or the VM admin to manually disconnect or reassign each VM to another EPG. Instead, you could just create a quarantine microsegmented EPG, define the attribute or attributes you want APIC to look for, and then associate the domain or domains where you want APIC to look into. As a result, the web server VMs, which would match the defined criteria, would be automatically assigned to this new EPG, and in consequence would be isolated since there's no contract defined for it. Once the thread is gone, we could simply delete or modify the microsegmented EPG, and the VMs would be back to their base web EPG, gaining communication again as stated originally through the contract. We will cover microsegmented EPGs in detail, as well as other use cases for them later in this module. With the knowledge you now have, you could also insert layer 4, layer 7 services such as firewalls between 2 different EPGs. For example, if you have a virtual or physical firewall running with 2 interfaces, also known as 2-arm, we could configure it to become the default gateway for both subnets, removing the subnet IP address on each bridge domain, making the ACI fabric behave as layer 2 exclusively. All your security policies and even routing would now be performed at the firewall level, making the contract less relevant in this configuration, since the firewall belongs to both EPGs on different interfaces. For this configuration to work, we would just need to make sure that ARP and unknown unicast settings on each bridge domain, web, and database are set to flood, since firewalls may behave as silent hosts. These settings are also needed when connecting to legacy switches, for example. We will explain ACI forwarding behavior, flooding, and endpoint learning briefly in the next chapter, so stay tuned. The potential problem with this scenario is that your firewall may become the bottleneck. This is yet another automation benefit with ACI, since contracts may not only have permitted statements as we saw, but we could also redirect traffic to layer 4, layer 7 devices using service graphs, which automates layer 4, layer 7 services stitching and enables you to use other cool features like policy-based redirection, which would allow you to redirect traffic to the firewall selectively based on rules. This can help you reducing the amount of traffic that hits your firewall. We will cover L4, L7 services in detail once we get to Module 4, so just know service graphs exist for now. There may be other ways of using EPGs and bridge domains. For example, you may assign multiple subnets to a single bridge domain, which could be associated to a single EPG. Still, the same fundamental rules apply. Therefore, it really does not matter that VMs are in different subnets. As long as they belong to the same EPG and there's routing, there will be communication. Taking a look at a second additional scenario. If we had the same bridge domain with the same subnet used in endpoints assigned to different EPGs, the same rules of the game still apply. Therefore, there would not be communication between both VMs in this example until a contract is configured. Although you could use different configurations as shown, I recommend you start by associating one dedicated bridge domain with only one subnet to each EPG you create. Finally, step 5. Before, we would configure a given interface with a routing protocol to peer with another router to provide external layer 3 connectivity to your network. Now, with ACI, we do it by creating an EPG called L3Out. We configure L3Out EPGs by selecting an interface, sub-interface, or SBI, as well as the routing protocol to run on a given leaf. Then, if we want the L3Out EPG to communicate with any other EPG, we will have to create a contract. For example, if we wanted the web servers in the web EPG to talk to the internet, we would need to create a contract between the web EPG and the internet L3Out EPG, allowing all traffic in this case. So, what are the differences between a regular EPG and an L3Out EPG? In a nutshell, IP and MAC addresses, which are known as endpoints, are assigned to EPGs, while learned prefixes from external connections are assigned to L3Out EPGs. Just remember we need a contract if we want communication between both worlds, and you should be fine. As a summary, with ACI you can start with a simple single tenant configuration as we just learned, or you can create multiple tenants, VRFs, configure VRF leaking and policies between them, and more, sharing objects and configurations. Build your design based on your needs and follow the best practices to make the most out of this powerful and flexible approach. If you remember these 5 steps to configure the logical network in ACI through the GUI, CLI, or API, you should be able to communicate pretty much anything over it.
ACI provides you with a better, simpler, and secure network, any size, anywhere, and on any cloud. If you want to learn more about other common tasks and how ACI radically simplifies network provisioning and operations, please watch the rest of the videos in this series. Thanks for watching.